Hello again. Today we want to talk more about hypothesis testing, and we're going to talk about testing one proportion. That's what we talked about the last time we met, which was in some cases yesterday. Testing one proportion, and then I'm going to go ahead and close with an example showing you how easy it is and how similar it is to make a test of the value of one mean. And so let's get started. And we mentioned M&M candy the other day, and there was a claim, actually it's a claim by M&M Mars, that 13% are brown. 13% of the M&Ms are brown colored. Now, we can make that into a statistical hypothesis, and it would be a null hypothesis because it contains the equal sign. And as a null, it would look like that. Now, is the claim at least 13 or no more than 13? Or no, it isn't. It's that the percent brown is 13. So that means since the alternate hypothesis has to be everything else, the alternate hypothesis would be P not equal to 13. And this is an example of what we call a two-sided test, which means that the critical value will be divided between the upper and the lower tails. Now, I think we want to establish a systematic way for doing these tests. And so in the system that I was teaching you earlier this week, the next thing we would do would be to declare an alpha. And let's just say we're using an alpha of 0.5 again. And then we remind ourselves of what our test statistic is. And we will remind ourselves again that if we're testing for one proportion, the test statistic is always going to be Z equal P hat minus P over P Q, that over N, and the square root of that piece. And so that's one thing you have to remember. We talked about how one would decide on a test statistic, but now that work's done, so all you have to do is to remember what the test statistic is. And really, you don't even have to remember it because you can write these things down, write them on note cards, and keep the note cards with you when you're doing these kind of tests. So we've got an alpha declared, and we've got a test statistic. Now we want to gather data, and so our data, I think I got this from Marty Triola, randomly picked 100 M&Ms, and we found, I'm trying to see how many we found, and we found, out of that 100, we found that there was 8%, or 8 out of 100 that were brown. Now, if we've got this much, then I think we can see what our observed value of Z was. So Z star would be, here's how we defined Z, the test statistic. Well, it's the sample proportion minus the proportion in the null hypothesis, and then the denominator is the proportion from the null and its complement Q, and the sample size, take the square root, and that's how you calculate Z. So the observed value of Z in our case is going to be 0.08 minus 0.13 divided by 0.13, 0.87, complement of 0.13. We said our sample size was 100, and we take the square root of that, and that's equal to negative 1.487. Now this is a two-sided test, often called, in fact, often by me, also called a two-tail test. Because if Z star falls in either tail a lot more than 13%, upper tail, or a lot less than 13%, lower tail, either of those makes me doubt the null hypothesis. So the critical region would be upper tail and lower tail. Any extreme value of p hat makes me doubt the null hypothesis. In this case, since you see this is negative, or you see that p hat is less than p, I would calculate the prob value as 2 times, now I'm multiplying a probability here by 2 because it's a two-sided test, 2 times the probability that Z is less than Z star, negative 1.487. And then we'll use Minitab to find out what that probability is. But why is it 2 times? It's because it's a two-tail test, and we have to account for the probability of Z observed being this far away in the lower tail or the upper tail. So we multiply by 2. And why is this a less than? Well, it's because the observation is falling on the low side. So we want the probability that it's this low or lower, that is Z less than. And that's how we calculate this p-value. And that p-value would be, I of course did this before class, and so I looked up the probability, the Z probability here with Minitab, or maybe I use my calculator, but it doesn't matter. The p-value is 0.1370. Now compare that to alpha. You see that p-value is greater than alpha, which was equal to 0.05. Therefore, we fail to reject the null hypothesis. Our sample of size 100 did not yield sufficient evidence to reject the claim that the population proportion is 13.13, 13% brown M&Ms. Now let's take a look at this same problem using the classical approach. That was a prob value approach, but we know there's also the classical approach. And if I was doing the classical approach, I'd start by drawing a sketch. And so let's sketch a z-curve. My z-curves are always a little bit shaky, but I mean well. And let's see if I can kind of extend that. Yeah, kind of like that. A two-tail test means that we're going to take our alpha and divide it evenly between the two tails. And so I want an 0.25 in the upper tail and an 0.25 in the lower tail. And this is going to be the critical value for the upper tail. This will be the critical value for the lower tail. This will be the lower tail critical region. This will be the upper tail critical region. So I guess the thing we probably should do next would be see if we can find what this critical value is. So this is a Z distribution. If I want, I could easily find, using Minitab, find this value, and by symmetry I know this one would be whatever this was with the opposite sign. So why don't we do that? Let me take just a second to get Minitab into our playing field here. Welcome back, Minitab. Now let's calculate probability distribution, and it's a z, so we'll say normal. And I want to find a point on the horizontal axis, so I'm going to use inverse cumulative probability. And my input constant, since I'm doing inverse, my input constant would be the area to the left, which would be 0.025. 0.025. So we'll say OK. And Minitab tells me that that critical value is 1.96. In fact, it says negative, doesn't it? 1.96. All right, what is that telling us? That's telling me that this critical value right here is negative 1.96. And by symmetry, this one would be positive 1.96. Now, if we're doing the classical approach, the next thing we would do would be to evaluate z star. Well, fortunately for us, we've already done that, and I see that there's the value of z star equals negative 1.487. And now all I need to do is to put z star into this picture. Negative 1.487, this would be 0 right here, and this would be about 1 right here, and somewhere right in here would be z star, which is the observed value of z, equals negative 1.487. Now what's our conclusion going to be? Well, z star is not in critical region. Therefore, we fail to reject H naught. It's the same conclusion. Well, it's always the same conclusion as what we get with the prob value approach or the p-value approach. And it's not necessary to do both approaches except for practice. Now, I hope that we've done enough problems, and I hope you've read your book, chapter number 8, and you've got a feel for how we do test of hypotheses for proportions. I want to consider another claim, a different sort of claim. And let's say that somebody has made a claim. Let me change papers here because I want to be sure I get this right. A claim that on average, Austin housing is no more than $390,000. So the claim is that the mean Austin house price is no more than 390,000, and we'll make that good old US dollars. So there's a claim. Now this one's not a claim about a proportion. This is a claim about a mean, and it's talking about the mean of a population. The population is Austin houses that are selling, and so I think we would say that the claim would tell us that the mean is no more than would mean less than or equal, wouldn't it? So the claim would contain equals, and therefore it would have to be a null hypothesis. So I think we're looking at a hypothesis mu, and I'm going to write it this way because this is just convention, 390,000. We could use units of 1,000 and avoid writing all those zeros, but we'll let it go for right now. And just to remind myself, I'm going to put a less than or equal to out here. And again, your author no longer does that, although he used to. Well, the alternate hypothesis is everything else, and so the alternate hypothesis would have to be mu is greater than 390,000. And as before, that is when we were testing a proportion, this greater than means that we're dealing with an upper tail test. Now, relying upon our experience with testing for proportions, what's the next thing we do? Well, we set an alpha value. So let's let alpha equal, no sense getting fancy right now, let's just let alpha be 0.5. That's very usual. And the next thing we need is a test statistic. Well, now here's where something new introduces itself. Remember, the test statistic has got to help me decide between the null and the alternate hypothesis. That's the first requirement. The second requirement is I have to know the distribution of the test statistic because I'm going to compute some probabilities. And if I know the test statistic distribution, I can compute any needed probability. If I don't know the distribution, I can't do that. So I'm going to just propose a test statistic. What if we would use as a test statistic x bar minus mu over, now I would say sigma here, except if we don't know the mean, we probably don't know sigma. So, but if we take a sample, we can calculate the sample standard deviation, S, and we could use the statistic S over the square root of n. So what I have done is to substitute S for the unknown value sigma. When I take a sample and estimate both mu and sigma and form this statistic right here, we know from past work, back when we were doing estimation, that that statistic will have a t distribution, student's t distribution, with the degrees of freedom equal to n minus 1. So it looks like this is going to be plenty easy since we know the distribution of the test statistic. Now, anytime we're making a test about one mean, we're always going to be using this test statistic. So there's not a bunch of things to remember. You just have to remember that when we're testing one mean, our test statistic is t, defined in this way. So what's the next? We gather data. So I'll just call that data. And suppose with me that when we gather data, we take a sample of size 150 houses. We randomly select 150 houses that have recently sold, and then we look and see what their selling price is. And so what we've got for data is 150 selling prices, and from the 150 selling prices we compute x bar is equal to, and in this case it was $390,939. And then we further calculate S over the square root of n. That's the denominator down here, and this denominator has a name. It pops up often enough. We call it the standard error of the mean. And you'll recall from looking at the results of descriptive statistics in Minitab that one of the things we can have Minitab calculate for us is the standard error of the mean. So Minitab will calculate this value for us, or it will calculate S, and we know n, so we could use a calculator and calculate this value ourselves. It doesn't matter how we do that. Either way, in this example, it was 1605. 1605, and so there's our data. Now we can do p-value or we can do classical. Let's just, for the heck of it, since it's the modern way, let's start doing p-value first. So we're going to make a decision based upon the p-value. Well, I think the first thing we need to do is to find the observed value of t. And that would be, now here's what t is. So x bar, where do we get x bar from? We get it from the data. So I see that x bar is 390,939. So there's x bar minus mu. Mu I get from the null hypothesis. So that's a 390,000 over sigma over the square root of n. That's the standard error of the mean and Minitab when we gathered our 150 values and put them in Minitab and said, what's the standard error of the mean? Minitab gave us the standard error, and it was 1605. So the observed value of t is equal to, just using the calculator, 1.56. So the p-value, now this is an upper tail test, and so the p-value is going to be equal to the probability that t exceeds t star is the probability that t is greater than 1.56 is equal to, and we'll use Minitab and the t distribution and calculate this probability as we have before, and this is going to be equal to 0.1209. That's greater than alpha, so we fail to reject H naught. Not enough evidence here to reject the claim. Now let's see what the evidence is. The claim is that the average selling price is $390,000, and we take a sample of size 150. That's a fairly good size sample, and we find that the average of our sample is 390,939, so about $1,000 over what this claim is saying. We find our average is about $1,000 more. That doesn't strengthen my belief in this H naught. But I know there would be, if I take a sample of size 150, I know I'm not going to get a sample mean of 390,000 every time. When H naught is true, sometimes my sample mean will be less, sometimes more. So the question is, how surprising is finding an X bar of 390,939 or more? And that's this probability that we calculate right here, and we find that this probability is 0.12. Given the truth of the null hypothesis, that's how we did this calculation, and the probability is 12%. That's not unusual. Unusual we defined as anything with a probability less than alpha, which is, we're using 0.5 as we usually do. So this probability is not one that surprises us. It's greater than alpha, so we fail to reject the null hypothesis. And that's pretty well going to use up the time we have for this lesson. So think about it, read your textbook, work some problems out of the back of the section, and you will get this. It is very similar to how we test for proportions, so that's the good news. The main difference is just the test statistic. That's just one thing to remember. What's the test statistic for a test on one mean? Well, it's a t statistic, and it's defined as you see right here. So have a good rest of your day. I hope everything goes well for you.